All right. Thanks everyone for joining us today. So my name is Derek Larson. I'm a design engineer in the Spokane office. Originally, this presentation was also going to be provided by Mary Opalka in our office. She did provide some upfront support on the content, but has since moved on to greener pastures in Alabama. Um, but anyways, want to give a shout out to her for her help in putting the content together with me. Um, Also, thanks to Tip and Kyle for getting this set up on the Seattle side, and to Seth Davis and Jeff Urich for providing some review as well. So today we're talking about high efficiency VAV systems. So what we'll talk about today: what is it? Why do we need it? Where do we need it? Meaning what types of spaces or buildings is this required? How is it different than a standard VAV system? What are the required provisions that you need to do to be compliant with high efficiency VAV? Pitfalls and traps to watch out for as you're designing these systems, and finally, applications in retrofit projects. So, what is it? So, in terms of what I'm calling classic HVAC design, so what we've done for years and years is we typically will provide the ventilation air through our primary air handlers, mix that with our return air, and then heat or cool it, and then send it out to the space. But the latest Washington and Seattle energy codes are requiring a separation of the ventilation air from the primary heating and cooling equipment. These two systems need to be completely isolated from one another. So this is only for certain space types, though, which the code lists as office, retail, education, libraries, and fire stations. And it should be noted that this is referring to space types and not building types. So if we're talking about an education facility, the gym, for example, does not necessarily need to meet this DOAS provision of needing to separate out the ventilation air, but the rest of the school would. So right now, this whole requirement, this is Washington specific. It's the Washington State Code and the Seattle Energy Code, but I'm not sure if maybe in other regions this might be coming soon. Anybody in other offices, or is anybody aware of this ventilation separation requirement coming? Doesn't sound like it. So what I'm calling here with new HVAC design. So what is the code requiring now? So I already mentioned ventilation. We have to serve and temper that through a separate dedicated system, or a DOAS. This is section C403.6 in both of the codes. And the intent here, the reason they want us to do this is if you have a system that's not calling for heating, not calling for cooling, well, we can save some fan energy by turning off those primary heating and cooling fans. Just let the ventilation fan run. We can also limit the reheat penalty that's going to be inherent with most multiple zone type systems. So a standard VAV system, for example, has some inherent reheat penalty that has to be paid. So talking about single duct VAV, we've been doing single duct VAV forever. I mean, we see it everywhere. It is a pretty efficient system, but the general setup of a single duct VAV system doesn't work well with this whole separation of ventilation air from the heating and cooling systems. And in high-rise buildings especially, this can be problematic. You think if you have 40 stories that you have to run your HVAC through, that's a lot of piping, a lot of controls. It's not very practical for that type of application. So we have this high efficiency VAV, HEVAV, which is an allowed exception to this requirement. So the code's saying, hey, you can do single duct VAV, but we're going to make you do it in an extremely efficient manner. And there's a list within the code, 16 things you have to do to say your system is high efficiency VAV. And some of these are pretty easy to meet, but others are fairly difficult, and you might run into some problems in trying to implement. So before we kick off, with those provisions, this is really more of an introduction, but it should arm you with the knowledge to know where to look, the things to watch for. But as you design one of these systems, you're going to have to do your own digging. This isn't going to make you an expert. These provisions are described in more detail in section C403.7 in both codes, and these are in addition to what's already required. So the code already says you need to do static and temperature reset strategies, morning warm-up. So the provisions to meet high efficiency VAV don't necessarily talk about those things, because those would be required for any VAV system, not just high efficiency VAV. And in terms of the terms that are used, so high efficiency VAV versus high performance VAV, I see these terms used interchangeably. I've always taken them to mean the same thing, but in terms of what the code says, they use high efficiency VAV as their term. All right, so let's hop into the things we got to do to be a high efficiency VAV system. So the first one is pretty straightforward. Air side economizer. You have to have an air side economizer, also known as free cooling, through your air handler. We've been doing this for years and years. This should not be much of an issue, but they are saying that you have to have it. And the intent here is let's provide free cooling when we can. If our outside air conditions are nice and cool, but we have a cooling load in the building, let's use that economizer. Let's avoid operating our chilled water and our DX systems. The second one, DDC system. So your air handlers and your terminal devices, your VAV boxes, they shall be controlled by a direct digital control system. Additionally, your terminal devices and your air handlers have to be able to talk to each other and be monitored by your end user. The intent here is if we have full DDC control of that system, it allows for better optimization of the system. If we can do custom sequences, which you're going to see are pretty much a necessity to meet some of the other provisions, having that DDC control gives you that capability. And the pitfall here is if you are looking to use packaged controls or onboard controls that come with the equipment provided by the manufacturer, you might have some challenges in meeting this provision, and there is definitely more to come on this on the control side. So here's an example of a DDC front-end automated logic. So this is looking at a VAV box. As an example of how this can assist with troubleshooting, you can see here the reheat is on, but we're only seeing a couple degree temperature difference across that coil. So this was an example of a failed VAV box, or failed reheat, rather. The third provision, outdoor airflow monitoring. So if your air handler has a minimum outdoor airflow of at least 2,500 CFM, you have to track that with an airflow monitoring station. Additionally, that airflow has to vary based on some VAV box feedback. So if you're doing demand control ventilation out in your space, and it also needs to account for changes in ventilation effectiveness. So if the majority of your VAV boxes are in heating mode, that's going to have a different ventilation effectiveness than boxes in cooling mode, and your system has to account for that. The code isn't explicit on how to account for that, but this is just describing the general intent. So a big point here is we can't simply just vary that outside air damper position based on supply fan speed, which I've seen many sequences that do exactly this. You balance it at the low speed, you balance it at the high speed, and then you just interpolate between the two. But no, in this case, we need to actually vary that based on some feedback from the VAV boxes. The intent here, so our minimum ventilation air that we're actually sending out into the building is constantly changing as the supply fan ramps up and ramps down, outdoor air damper opens and closes. You have an infinite amount of permutations where you don't really know how much ventilation air you're bringing in. And so if we have that airflow monitoring station, we know how much outdoor air we're bringing in and if it's excessive. And just as a general reminder, anytime we're tempering outside air, that takes a ton of energy. If it's 0 degrees outside in the middle of winter, which we can get there in Spokane, that takes a ton of energy to heat that outside air up. So anything we can do to reduce that intake can save us a lot of energy. Next up, we have supply airflow monitoring. So this has the same trigger as the previous provision. So if our minimum outdoor airflow is 2,500 CFM or greater, we also must track the supply airflow. As far as the savings intent, this is going to assist our building operators in troubleshooting. For example, if we have a discrepancy between our total air handler supply and our total VAV box supply airflows, this will help bring attention that, hey, something is wrong. Additionally, this allows monitoring of the relationship between outside air and supply air, in terms of what percent of supply air is outside air. And this is going to be useful in meeting some of the other provisions that are to come. And so to the right there is an example of a Ebtron Gold flow meter, which would be a fairly common airflow monitoring station. Maximum served area. If you have a VAV air handler, any one air handler can't serve more than 50,000 square feet. Only exception being if you have a single floor greater than 50,000 square feet, then it can serve that entire floor. The intent here is if we can limit the square footage served, we can prevent excessive duct runs throughout the building, which does a couple things. It reduces the required supply and return fan brake horsepower, so we can downsize our fans at the air handler to serve that space. And it reduces the distribution temperature losses within the duct. So if we're sending cool air down that duct, the further it has to go, the more temperature, the more distribution losses you're going to have on its way there. Additionally, if we can break that system into multiple units, we can prevent over-ventilating the entire building. So if you have one or two conference rooms that are driving the ventilation requirements, if we have fewer units, there's less chance that that's going to over-ventilate the entire building. It may over-ventilate one section of it a bit, but it will limit that from happening. So primary airflow for interior spaces. So if you have a VAV box serving an interior zone, meaning any zone that does not have an exterior wall exposure, you have to size that box to serve the full cooling load at a supply air temperature 5 degrees greater than the design supply air temperature for exterior zones. So as an example, if we design our air handler to provide 55 degree air on a design day, on our interior zones, we need to assume that those are actually getting 60 degree air. The intent here being prevents our interior zones, which almost always need cooling, from driving the entire system to a lower supply air temperature set point. So really, that's going to optimize our temperature reset strategy and reduce that reheat penalty, which again, that's one of the big reasons for the DOAS provision of the code is they want to limit this reheat penalty inherent with these types of systems. The pitfall here, and this is a pretty big one, those interior zones need to be designed for 33% more airflow, thereabouts. Since our air is 5 degrees warmer, we need to provide more of it to serve the same load. And so where that comes into play is in sizing our ducts. So if you're going to, so we need to make sure we're sizing our ducts appropriately for that additional airflow. And it's not just in the branch duct to the VAV box. I mean, that's going to reverberate all the way back into the duct mains, all the way back to the air handler. So if this is missed, this turns into a pretty big deal. So our inlet velocity on our VAV boxes. So if we have a VAV box with a minimum airflow of at least 50% of design, so that would be considered a relatively high minimum airflow, we need to select our box with an inlet velocity no greater than 900 feet per minute. And what this really means is that this is oversizing the inlet compared to a typical VAV box design. The intent here is we can reduce issues where our static pressure reset control strategies is driven by boxes that have high minimum airflow. So you can get in a condition where you have a handful of boxes that have these high minimum primary air set points, they end up driving the entire system. But if we can oversize those boxes a bit, then that'll allow us to reset down to a lower pressure set point. And ultimately, anything we can do to optimize that reset strategy can save a lot of fan energy. So just to visualize it, here's the typical VAV box. On the inlet, we're saying can't have more than 900 feet per minute. Typically, you'd be in the range of 1,500 to 2,500 on a standard VAV box design. Sequence design guidelines. So your DDC sequences shall be designed per the guidelines of ASHRAE Guideline 36, High Performance Sequences of Operation for HVAC Systems. The intent here, hey, let's just make sure our systems are operated efficiently per ASHRAE recommendations. But a warning here, this guideline was just published about a year ago, and it's still undergoing review and changes. And a few of us have taken a look at this, and the trap we're seeing here is just looking at this standard and what they tell us to do with a VAV system is very confusing. Some information conflicts or seems to conflict with other information in the standard. It doesn't quite feel like the standard is quite ready for prime time yet. But as you're designing these systems, it's definitely will be useful to use as a reference. Just tread carefully. Allowable fan brake horsepower. So the energy code typically has a maximum allowable fan horsepower allowed based on the airflow you're providing. So if your system is providing 10,000 CFM of air, there's a maximum allowed horsepower allowed to deliver that amount of air. But for high efficiency VAV, it says you can't exceed 90% of what's normally allowed. So if you're normally allowed a 20 horsepower motor, now you're not supposed to exceed 18. The intent here, let's reduce our fan power through upsizing our ductwork or selecting more efficient fan impellers, or maybe we can make sure we're using fittings that have less pressure drop than our standard fittings. Anything you can do to reduce that static pressure and reduce your fan horsepower. But make sure you're doing that calculation correctly. We've seen this many times where the allowable horsepower calculation is not done right. The main issue is usually we're either not taking advantage of credits. So if you have a system, for example, with a high efficiency filter, you are actually allowed more horsepower because you have that filter that's going to have more pressure drop than a standard filter. But there's also some penalties. There are some things that will penalize you, and they say we're not going to give you as much because of X, Y, or Z with that system. So just making sure you know how to do that calculation can save you a lot of headache, especially on making sure you're taking advantage of any applicable credits that are going to help you. VAV box EC motors. If we have any fan-powered VAV boxes, these have to have electronically commutated motors, or ECM. Additionally, your box fan speed must also vary with both the heating and the cooling load, which is a little different than what we're used to. So back to what I'm calling classic fan-powered VAV design, usually these fans are constant volume fans. They're either on or they're off, so you're getting full airflow or nothing. The intent here, EC motors, just right out the gate, they're more efficient than standard PSC motors, but we can also save some fan energy by varying that box fan speed with both the heating and the cooling load. And so just to visualize that, so here's a classic series fan-powered VAV design. So we have our three operating modes, heating, deadband, and cooling. In classic design, that fan motor speed is just going to be constant speed. It's just running. Anytime that space is in occupied mode, that fan is just running full out. But with high efficiency VAV, what we need to do is we need to vary that fan speed with the heating load. So at a high heating load, our fan speed will be high, and it'll drop off as we approach the deadband. In that deadband zone, we're going to be at some minimum speed, and then it's going to increase on the cooling load side as our cooling load increases. Fan-powered VAV applications. We can only use fan-powered VAV boxes at our perimeter zones, zones with an exterior wall exposure. All other VAV boxes on that project shall be standard single duct terminal units, so they won't have any fans. The intent here, typically we don't need fan-powered VAVs for our internal spaces that have these really low envelope loads. Typically they're just not necessary. So let's save some fan energy. Let's get rid of fan-powered VAV boxes wherever we can. But it is important to have a solid morning warm-up sequence for any of those interior zones. So sometimes those interior zones can have trouble heating up in a morning warm-up cycle without that fan assist. So you might have to get creative with your sequence to allow the boxes to increase to a higher primary air set point just to get better air distribution. So just something to watch out for. And just to visualize that, here's an example of a VAV system we designed where we have an exterior zone. So that's going to be a fan-powered box because that south exposure with all of that glazing makes that a perimeter zone. And then all those VAV boxes on the inside for our interior zones, those are just standard terminal units with reheat. Fan-powered VAV primary air reset. This is another one that's a little unusual and might be a little difficult to implement if you're used to standard VAV design. So if you have a fan-powered VAV in occupied heating or in deadband mode, we have to reset the minimum primary airflow set point. So again, talking about classic VAV design, usually that minimum airflow set point is just a fixed value. So maybe it's a 100 CFM. We just don't ever allow it to go lower than that 100 CFM minimum set point. But in high efficiency VAV, we have to vary that minimum dynamically. And that needs to vary as a function of the air handler unit, outdoor air, ventilation fraction. So as our supply fan is ramping up and down, as our outside air damper is opening and closing in response to DCV or ventilation effectiveness, our outdoor air percent at any given time is going to be a variable value. So if our outdoor air percent at the air handler increases, meaning more of our primary airflow is outside air, we can actually drop our primary airflow set point. We're going the other direction. If our outside airflow percent drops, then we have to raise that set point. We have to provide more air to deliver the amount of ventilation air required by ASHRAE 62.1. The intent here, only provide the minimum amount of ventilation needed. So if a fixed primary airflow set point, minimum set point rather, is not optimized for all operating conditions. There are many times there where we can reset that primary airflow set point and have a more efficient system than standard VAV. High occupancy spaces. This one's pretty straightforward. So if we have a high occupancy space, greater than 150 square feet, designed for more than 25 people per 1,000 square feet, we have to do all of these things. It has to have a dedicated VAV box. We have to do demand control ventilation based on CO2 levels. And we have to tie it into occupancy sensors that will set back a minimum of 5 degrees in heating and cooling whenever that space is unoccupied. The idea here, make sure those high occupancy spaces aren't driving the entire system, and that's kind of a recurring theme where we don't want one or two spaces driving our reset strategies. And often these high occupancy spaces are periodically occupied. So what we design it for is really not what it's going to need 90% of the time. So let's only provide what's needed when it's needed. High process load spaces. So if we have any spaces with process cooling loads, greater than 5 watts per square foot, which is a decently high value, these have to be served by separate and independent HVAC systems. So the typical application here would be server rooms and data closets. We may use the VAV system for backup cooling only to offer some redundancy, so if that separate independent system goes down, they can still cool that space. Additionally, that process load HVAC equipment has to have an airside economizer, or you need to recover that process load energy to use somewhere else. You need to recover that heat. The idea here, again, we don't want to prevent operation of the entire VAV system to only serve these isolated constant load zones. This one space is going to end up driving the entire system, and we don't want that to happen. Central plant requirements. So typically in a VAV system, we will have a central plant. And for high efficiency VAV, we need to meet one of the following two options. So the first option, in our hot water plant, we have to have a hot water system served by either high efficiency gas-fired boilers, air-to-water heat pumps, or heat recovery chillers. Probably the most common application we would see is high efficiency boilers. We see condensing boilers all the time, but the point is they want that hot water plant to be efficient. So we need to either meet that, or on our chilled water plant, our central plant has to be served with chillers with IPLV values 25% higher than what's required by code, and have a 5-to-1 turn down or 20% chilled water storage. So we only need to meet one of these two. An important note here, the code's not explicit, but electric reheat is not allowed. At least this is per the energy code. I forget the team. There's a technical support team, code technical support team in Seattle, and they say electric reheat does not meet the intent of high efficiency VAV, even though the code is not explicit about that. And that makes sense. I mean, electric reheat is not a very efficient way to do things, considering the alternatives. So just an important thing to note. The intent, let's reduce our central plant energy use by going above and beyond what's actually required by code, and avoid that high cost and high energy use of electric reheat. The last provision, controls. So I mentioned controls was going to come back. And if you look at the code, this single provision takes up an entire page. This one provision, put in quotes, this single provision is actually 8 mini provisions. So there's 8 things that this one provision is asking you to do. We have to monitor our outdoor air supply air and return air temperatures. Our temperature sensors have to meet a minimum accuracy requirement, as described in the code. We have to have a number of status indicators. Free cooling is available. Economizer is on. Compressor's on. Heating's on. Our mixed air low limit cycle is active. And the current value of each sensor. We have to have the capability to manually initiate each operating mode to assist with CX and FPTs. So our commissioning team, if they need to simulate economizer operation, they need to be able to do that, or reset strategies, or anything, really. They have to have that capability to manually initiate them. The system has to be configured to communicate any faults or alarms to an accessible location. So typically that'd be the DDC front end or locally at the thermostats. Not at the air handler interface, especially if this thing is up on the roof. You shouldn't have to go up on the roof to look at your faults and alarms. It has to be reported to an accessible place. You have to have a specific sequence in place for every VAV box where once a month you drive them open, drive them close, you check the airflow values at each position to make sure that box is working. Make sure those inlet valves are working and actually modulating the way they should. And your VAV boxes have to tell the system when its respective zone is driving our temperature and duct static reset strategies. So usually you end up with one or two boxes that are usually the worst offenders, and they're kind of driving everything else. Um, and your system has to be able to report and trend when that is happening for every VAV box. And the operator has to be able to exclude those boxes from the logic. They don't have to exclude them, but they have to be able to if it's causing a problem with the rest of the system. And lastly, we have a number of faults and alarms we need to detect and report. We have to say when a temperature sensor has failed, when we're economizing when we shouldn't, or rather, not economizing when we should, economizing when we shouldn't be. Outdoor air or return air dampers not modulating as they should. If we're bringing in excessive outdoor air, and if our VAV has a primary air valve failure, as noted by that sequence on the previous slide where we're driving the box open and closed. So these 8 requirements of this one provision. This is a lot to do. This is a lot to ask your control system to do. And so again, this makes it really difficult to achieve high efficiency VAV with a packaged control system. Maybe even impossible. I'm not aware of any manufacturers who could meet all of these requirements. Even if we have a backnet connection, you're still very likely dealing with some canned control logic that you're going to be stuck with. So you're very likely going to need a full-blown DDC system with custom sequences to achieve all of these provisions. And the intent here, by doing all of these things, this really empowers the maintenance personnel to identify and fix problems before they end up wasting a bunch of energy. We don't want something to fail, something to go wrong, and then they don't find out for 6 months. And by then, they've already wasted a lot of energy. This really just gives them the power to prevent that from happening. So that's everything we got to do. So let's close out with talking about retrofits. So this is kind of near and dear to me because I mostly design for the energy group where we're doing retrofits all day, and we're looking at existing VAV systems, and the question often comes up, hey, can we turn this into a high efficiency VAV system? Ultimately, retrofitting these existing VAV systems can be extremely difficult to meet all 16 of those provisions. The main reason being several of these provisions are related to the design of the HVAC distribution infrastructure. So talking about ductwork especially, it's not just controls, which seems to be a common misunderstanding, is you just need to control it in an efficient manner. No. So thinking back to designing our interior zones for 5-degree warmer air, well, now we have to upsize all of that ductwork. Or the brake horsepower limitation capped at 90% of what's normally allowed. That's another thing where maybe the existing ductwork, you just can't achieve that. So really you need to start a design from the ground up, or at least that certainly makes things a lot easier. But that said, existing VAV systems can very likely be retrofitted and replaced without meeting all of these provisions due to existing building exceptions. So there is code language on existing buildings that says we won't make you tear out something that is already installed and met code at the time of installation. So that would include all of the ductwork out in the system. So you can make a pretty strong argument that you shouldn't have to turn a existing VAV system into high efficiency VAV, but you may get a code official who is just really adamant and is going to fight you to make this happen. So ultimately, it's good to be proactive about talking to that code official on any VAV retrofit project. Because if you get down the road, you get towards the end of the design, assuming you don't need to do this, and then the code official is going to try and make you do it, that's a pretty substantial change in design that you don't want to have happen at the 11th hour. So the bottom line here, be very careful making promises to clients about retrofitting an existing system into high efficiency VAV. Again, it's not just about controls. There's a lot to it, a lot that needs to happen in order to meet all of these provisions. And unless you have an understanding and have gone through this checklist of everything that's required, it's really not that easy. It's extremely difficult to do. So that's all I got. Do we have any questions?
Hey, Derek, this is Daniel. I was kind of wondering about, I got in here a little late, so I apologize, talking a little bit up front about the verbiage under C403.7, where it says this exception shall not be used as a substitution for GOAS. So, I mean, it's not something that you can just go into high efficiency VAV for the sake of doing it because you don't want to do DOAS and stuff, right? I mean, so how does that language apply to wanting to go to high efficiency VAV, or the applicability of doing this for a new design?
I'd have to
Does that make sense?
Well, I'd have to recheck the specific language of the code. Yeah, my understanding was this high efficiency VAV is listed as a specific exception to needing to meet the DOAS requirement. Is that not your understanding?
That was my understanding.
Right, but let's see. But so the verbiage, and this is the part where I never really fully understand. I read it a couple of times, I've never really dived deep into it. So it says, in parentheses at the end of that section, C4 3.7, it says, this exception shall not be used as a substitution for a DOAS per section C406.6 or as a modification to the requirements of standard reference. So
I'm wondering if the C403.6 might have additional language regarding that.
Yeah.
Yeah, C406 is the additional efficiency package options where you have to choose 2 or more out of the 8. And so you can't take double credit for high efficiency VAV against one of these other options. They're just not letting you double dip. But it is still an alternative to a DOAS system using exception 2 of the DOAS section.
Okay.
Oh, yeah, that makes sense. Thanks, Jeff.
Derek, this is Sarah. Question for you about the variable flow on the fan power boxes. So you said it requires you to vary flow in both heating and cooling. Is that correct?
To vary the fan speed, right, on a fan powered box.
Okay. So I have more experience in parallel than series, and in my experience, often you would go to parallel boxes because of the benefit of when you go into heating, you can do constant volume to ensure that no matter what your supplier temperature is, you're getting good throw across your diffusers because they're designed for a peak flow. So that's just to watch it, that if they're not gonna, I understand the intent of the code, but it's fighting a little bit like good practice for how to run your parallel boxes. And they're just gonna dribble out hot air when it's in low flow. So it's kind of an interesting choice. And maybe there's a way you could vary the flow, but make the min flow on the heating side a little higher than it might be on the cooling side. I don't know.
That would probably be the way to do it. And what's kind of interesting is the code is not super explicit. Well, it's really not explicit at all.
Vary it, maybe.
Right. I think all it says is you have to vary the flow, but it doesn't tell you to what. To what minimum do you need to go down to. There may be something more in ASHRAE Guideline 36 that might have some more info on that.
Sure.
Or that could just be something that is, there's some room for interpretation on how you design it. It is a little surprising that is open-ended, seemingly open-ended, even though everything else in this whole high efficiency VAV section is just so strict.
I have another, it's more of a comment than a question. So 50,000 square feet, where you can't serve more than 50,000 square feet at a time. It's just, again, it's kind of a flag that for our larger buildings, that's actually fairly small. And so on one hand, we're having to design this fully custom air handling unit system with DDC controls. On the other hand, we're not getting the benefit of scale, where maybe you're gonna put a monster VAV unit on the roof that's fully custom, but at least you only have one of them. So it's sort of like, again, I totally get the intent of the code and the energy benefits to that, but there is an additional cost associated with that some of our clients might not, it might not follow our usual dollars per square foot rule of thumb benchmarks, if that makes sense.
Oh yeah, absolutely not. I mean, if you're going to look at a high efficiency VAV option, you'd probably throw that dollar per square foot stuff out the window, for a
Sure.
standard VAV system.
Exactly.
Yeah.
I've got a question more for the general group. How many of these provisions are more, McKinstry best practice, or how many of these are requiring us to go above and beyond what we typically design around? Derek, do you have a good feel for that, or does anybody?
I'd say a number of them would be probably above and beyond what we typically do.
Gotcha.
Especially some of the things like resetting the primary airflow minimum set point based on outdoor air percent. I was I was actually talking to Jeff yesterday about going over these, Jeff Urich, and he said, in his opinion, this is probably uncontrollable.
Right.
Just based on all these things we have to do. There's a lot of things here you got to control. And I guess that kind of brings me to another point of you may have to hold the controls contractor's feet to the fire to really make sure they actually do all these things, because I know sometimes the controls contractors can get a little loose with how they're interpreting your sequence and say, well, we have some kind of reset strategy. Maybe it's not exactly what you wrote, but in our opinion, this meets the intent. And on most projects, that's probably fine. But on these, you're probably going to have to be a little more critical and also have a conversation with the commissioning agent to make sure they know, hey, we really got to meet these things.
I'll say, from my perspective, they're all good practice, but doing them all on one project would be sort of out there. And also, they're all good practice in that you can design with the intent of achieving all of these, but we wouldn't necessarily have to have documented every single one. Whereas if it's for a prescriptive energy code, we would need to, which is a whole bunch of work and calculations, verifying things like, am I getting my 90% of fan power and stuff like that. Whereas maybe you could do fan power sizing much more prescriptively if you didn't get into that level of detail. Also, I'll say the application is kind of niche. Like if you don't have the stomach to go with DOAS, but it's a project big enough to do VAV, high efficiency VAV, it's probably also a project big enough to do whole building energy modeling, in which case you throw all this stuff out and start over type of thing. So it's like, it's a weird, it probably applies to some very specific conditions.
So Derek, did we ever figure out if anybody in our group has ever deployed this or tried to comply with this code?
I'm not aware of anybody who's taken one, to full constructed completion.
Yeah.
All right.
Yeah, it doesn't look like we have any more questions on this side, so nothing on Skype. I guess thanks for your time, Derek.
Thanks, Eric.
All right.
Thank you.
Thank you.
Thanks, everybody.